Good afternoon, class. This is lesson 2.1 for biology. The title is The Nature of Matter. I gotta say, as you look at this image, something about this picture is not quite right, but I'll leave you to figure that out. Anyways, as we move into chapter 2, we're taking a look at the chemistry of living things. And all living things are made of molecules. And guess what? Those molecules are made of individual atoms. And those atoms we study in the world of chemistry. So as we look forward here, our learning objectives for this section. First, identify the three subatomic particles that make up atoms. Then explain how all isotopes of an element are similar and how they are different. Explain how compounds differ from their component elements. We'll take a look at a few different compounds. And lastly, describe the two main types of chemical bonds. There's three kinds that we talk about in future science, but for right now, we're just going to dive into two of them. So to begin with, we have our good old atom. And as freshmen during your physical science course, you learn about atoms and the different subatomic particles that make up atoms. And you can see here we've got the protons. These have a little plus sign because they are positively charged. Electrons, they have a little minus sign because they are negatively charged. And the neutrons, they have no sign because they are not charged. They're neutral. So that being said, as we look at these different molecules, protons and electrons, they have to balance out. This example here, you can see we have 6 protons, we have 6 electrons. So this is going to be a molecule of carbon because we have 6 and 6. And we learn about this and we learn about the number of subatomic particles all through the time we spend studying these different molecules. Let's keep moving. Inside there, we also have some neutrons. These neutrons are not electrically charged, but they do give some of the mass to the atom. So this atom is going to have a mass based off of the number of protons and neutrons. The electrons have a little bit of mass, but it's kind of negligible. And they're going to have a charge based off of the proton to electron ratio. So if we have even numbers, we're going to wind up having a neutral atom. If we have uneven numbers, like more protons or more electrons, the atom's going to be positively or negatively charged. Continuing. Each individual atom is actually what we call an element. And an element is a pure substance that consists entirely of one type of atom. This one here, you can see we have a pure substance, one kind of atom in an element. This atom in particular has an atomic number, and that atomic number is going to be the number of protons. How many protons do we see? 1, 2, 3, 4, 5, 6. The atomic number here is 6. And as you can see, it is neutral. It is not a charged ionic particle, but has the same number of electrons as it does protons. So there is no charge on this particular atom. Continuing on, well, we get some special ones like isotopes. An isotope is a molecule, or I should say an atom, that has a different number of neutrons than most of the other atoms of this element. The example here is carbon. Carbon, as I mentioned, is the atom that has an atomic number of 6. There's a picture of normal looking carbon. There are 6 electrons, there are 6 protons, and there are 6 neutrons. However, sometimes we get a different number. And if we look at the chart here, if we have 6 protons, we're going to have 6 in any of these because the number of protons is what signifies which particular atom we actually have. If we had 7 protons, we would no longer have carbon. We would have something else. If we had 5 protons, we would no longer have carbon. We would have something else. So 6 is the number of protons. However, we can have a difference in electrons. No, actually, electrons should be the same as well. The difference is going to come in the number of neutrons. Carbon-12 has 6 neutrons. And if you add the number of protons plus neutrons, 6 plus 6, that's where we get this little 12 after the word carbon. It's non-radioactive, which means it does not decay. The next one up the ladder is carbon-13. This has 7 neutrons. It's also non-radioactive. When we get another neutron, when we get to the 8 neutron range, now we're looking at a radioactive isotope of the molecule carbon. We call this carbon-14. So when looking at carbon-14, as you can see, it has 8 plus 6, so that's 14. That's where the 14 at the end of carbon-14 comes from. Looking at isotopes, especially in the biology field, we're mainly talking about how we can use them to study living tissue because they do moderately small amounts of damage, but allow us to track and monitor where they are located. Let's keep moving. Chemical compounds are substances, I should say, that are made up of a combination of two or more elements in definite proportions. And there's several of them you have probably heard about or learned about. Water is one example. Carbon dioxide is another example. Later on in the week, we will actually get some models out and build a couple of these. The properties of these compounds are typically very different than the properties of the elements that make them up. What does this mean? When we look at the molecules that make up something like salt, okay, here's the next one, salt, sodium chloride. When we look at what makes up sodium and what makes up chlorine, sodium in and of itself is a very, very reactive, soft metal. Chlorine is a yellow poisonous gas. However, when we combine them together, we get table salt. And table salt is not reactive. It dissolves in water. It's not explosive when you put it in water. And so because of that change, we wind up getting a very different result in our chemicals. And that's what chemical compounds do. When you join molecules together, you get something very different. Another example would be water, H2O. H2O is made of two hydrogens and one oxygen. Well, as you probably know, on Earth, hydrogen is a gas and oxygen is also a gas. However, when you join them together at room temperature, they become a liquid. Moving forward into ionic bonds, you can see here on the ionic bond chart, we've got sodium and chlorine. This little squiggle line shows that we are going to be moving one of these electrons off of sodium onto chlorine. So right now, our sodium has 11 protons and has 11 electrons. This means it has no charge. Our chlorine atom has 17 protons. It has 17 electrons. It still has no charge. However, in the picture to the right, we have now removed this outermost valence electron from the sodium atom, and we have given it to the chlorine atom. No longer will the number of electrons and protons equal. So now we've got 10 electrons around the sodium ion, which means we have a charge of +1. So sodium ions have a charge of +1. The chlorine ion has 17 protons, but it picked up an extra electron. It is at 18 electrons, so it has an overall charge of -1. We did an example like this in the interactive, and if you don't recall how to do this, please check back on that. So we move forward then. Since we have a form of bonding called ionic bonding, this is where we are losing or gaining an electron. That's one type of bond. We have two that we're talking about. The second one being covalent bonding. Covalent bonding, like I mentioned with water molecules, is where the electrons are actually being shared by each of these atoms. So we've got a big old oxygen atom there. Oxygen has 6 electrons in its outermost shell. Hydrogens each have 1 electron in their outermost shell. And so because of the fact that they are sharing an electron, if you count the outer ring around oxygen, you'll see that there are 8 electrons. So oxygen's outer shell is happy. And if you count the number of electrons in hydrogen's outer shell, it has 2. That also makes the hydrogen happy. It's going to be stable in this form. So as we share these different electrons, we wind up getting 8 electrons in the oxygen. And our grand total here for oxygen is 10. 2 on the inner, 8 plus 2 on the outer. And so the oxygen is good to go. It's all the way set up how it wants to be. Same, like I said, is true for the hydrogen. It has as many electrons in its outermost shell as it can have and be full. So covalent and ionic bonding is kind of the name of the game, but we have one more little very weak bond. We call this, we call this the van der Waals forces. These kind of come into play with hydrogen bonding as well, because these are intermolecular forces of attraction due to a slight attraction between oppositely charged regions of nearby molecules. So if I pop back to this water molecule, the top end, the oxygen end of this water molecule has a slightly negative charge, and the bottom end of the water molecule has a slightly positive charge. You can see the electrons are all kind of surrounding the oxygen, and on the bottom part of these hydrogens, there is not a lot of electron charge. So there's slightly negative charge. Because of that, we get these van der Waals forces. Van der Waals forces allow for organisms like this, I believe it's a type of gecko, to hang on to different substances like completely flat glass. It can hold on to there because of these forces that are found within its toes and the ability of these different cells on the ends of the toe to actually bind onto and kind of closely hug to glass and other substances as it climbs. So that being said, we talked a little bit about forces here. So hopefully you're able to pick up the two different kinds of bonds we have and how we're going to take a look at molecules and elements and atoms and how they go together. So for this section here, you actually have a couple of review questions. Question number 1, describe the major subatomic particles that make up an atom. So make sure you describe all 3 of them. Question number 2, explain why isotopes of an element have the same chemical properties. Remember, it has to do with the number of protons in those isotopes. Number 3, compare the physical and chemical properties of compounds of those elements of which it is composed. And number 4, what are the differences between ionic bonds and covalent bonds? One of them is stealing or giving electrons. The other is sharing. Which is which, and explain why. So that is it for the Chapter 2, Lesson 1 lecture. If you have any questions, feel free to email me. Otherwise, I'll see you in class.